Hi, it's Nicholas Thompson. I'm CEO of The Atlantic, and this is The Most Interesting Thing in AI, a podcast produced by Rethink, The Atlantic's creative marketing studio, in collaboration with PwC, a leader in helping organizations use AI. In each episode, we're exploring how artificial intelligence is reshaping our lives. We talk a lot about the ways AI is changing the world, but what about how it's changing space? Today, I'm talking to Tory Bruno. He's the CEO of United Launch Alliance, a collaboration between Lockheed Martin and Boeing, which launches rockets deploying satellites and other payloads for companies like Amazon, as well as for the U.S. government. I wanted to ask him about how AI is helping us get into space faster, safer, how it's helping us build better rockets. And then I also wanted to ask him a little bit about life on Mars, communicating with extraterrestrials, other stuff that is endlessly fascinating and on which he has some very strong views. After I finish with him, I'm joined by Joe Schurman from PwC, co-lead of the firm's space program. We're going to talk about AI and the space economy. But to start, here's my conversation with Tory Bruno. Tory Bruno, so nice to see you here.
Great to see you, Nick.
This will be a lot of fun. I want to get into how AI is used in designing your rockets and how it could be used in the future. I want to talk a little bit about extraterrestrial life. But before we get to that, let's start with you. So you've been interested in rockets since you were a kid, and I believe you built your first when you were 12 or 13. Tell me about that.
Oh, my gosh. Well, actually, it was probably nine.
Okay.
And I grew up on a little bitty ranch up in the Sierras near Lake Tahoe. And, summertime, mischief. I found this case of like 80-year-old dynamite in the back of the barn. And obviously, the only thing to do with it was to cut it open, pull out the propellant, jam it into some old pipe I found, and try and make rockets.
Can I ask you, how many fingers do you have? Do you still have 10?
I still have 10. I'm very proud to say that some of my rockets got a good 10, 20 feet in the air before they exploded.
So at 9 years old, how did you know the mechanics of a rocket? And how did you know to put dynamite in a pipe?
Yeah, well, first, I was super fascinated by rocketry because I was just old enough to have watched Neil Armstrong walk on the moon. And so that was everything. I was all about it. We didn't have the internet, but we had libraries. So, I went down and I checked out books and I read and did my best. I didn't understand nozzles, but I did know that something, burning and energetic had to go in a big tube.
Wow. Okay. So you launch your first rocket. You amazingly don't blow up your barn or blow up your house.
Or die.
Clearly, by the fact that you're here, we've ruled that one out. Tell me how you get into the industry.
Well, I loved growing up on the ranch. Great place for a kid, but, no work for a rocket scientist. So when I had saved up enough money, I went down to Cal Poly, California Polytechnic University. I got a engineering degree and went straight to work for Lockheed back in the day.
And then how many years did you work at Lockheed? A couple of decades?
I spent 30 years at Lockheed.
Wow.
And then I've been here another 10 or 12.
You've been at ULA. And have you been running ULA for 10 or 12?
I have.
All right. So ULA has had a good run recently. Tell me what has changed to the company and why you're launching more than you used to.
Yeah, giant transformation for us. When I came here, I'll be honest, we were a monopoly. There was only one company in the country that could fly all these missions, primarily for the government. Suddenly, the industry had grown up. And so my mission was to change ULA, to transform it, and then develop this new vehicle we just brought into service called Vulcan. There's now commercial business and military business in space. We won a gigantic contract with Amazon just like a year or so ago, and we're now flying for them. We're going to go to about twice a month with this very exotic high-energy rocket, and we'll be hitting that tempo before the end of the year.
So when you started at ULA, was that right about when competitors started to get things into space and sort of, I was going to say light a fire, but that seems like the wrong phrase, light a fire under the rocket industry?
We don't like to use the words fire or explosion unless we really mean it. But that's actually why I came, because suddenly there was a competitor. It was SpaceX. They had a rocket. They weren't flying it very often, and it wasn't super reliable yet. The other thing that was going on is our main rocket, the Atlas V, had a Russian rocket engine on the booster, which we had because the government wanted us to. They wanted to keep all those Russian rocket scientists from wandering off to North Korea at the end of the Cold War. But at that point, now things were different. Russia invaded Crimea for the first time. People decided in Congress, get rid of that Russian rocket engine, and they actually outlawed it. So as I'm walking into the job, there's competition, which is good for the country, but a big challenge for a company that hasn't had any. And our main rocket was against the law, and basically we were going to close in 2017. And so my job was to turn all that around and, get a new rocket.
Let's talk through rocket launch and explain what the hardest problems are and why it is that you've been able to solve them in recent years, but hadn't solved them 10 or 15 years ago.
So we're going to talk about space launch vehicles, going to space and taking payloads there. But at the end of the day, you've got two kinds of rockets. Rockets that are most efficient and designed specifically to go to LEO, low Earth orbit, which starts about 100 miles up, and almost all the payloads are no more than about 600 miles up. And then you've got the other kind of rocket that is designed to take a payload all the way to what we call a high-energy orbit, like geosynchronous orbit, 22,000 miles above the surface of the Earth. Both kinds of rockets do it with stages. If we're a LEO rocket, the first stage burns out when you're still inside the atmosphere. You hand that job over to the upper stage. That goes up to low Earth orbit, lets the satellite go. And it'll either stay there or it'll fly itself with its own propulsion to some higher orbit. The high-energy rocket flies all the way into space. So like 2-3 times higher, 3 times faster, separates there because it wants to deliver an upper stage and satellite all the way in space. The big challenges are just the tremendous complexity of these machines and the energy they carry. A rocket like mine, it's sitting on the pad with 3 million pounds of propellant. Mm-hmm. Everything's got to work. Very few things can fail. And so you have this incredibly powerful, incredibly complex, unforgiving machine. Any little thing goes wrong and it's a giant fireball.
How much has the propellant changed? Are you able to get lighter, more efficient propellant, or has that stayed pretty much the same?
The propellants have been pretty much the same for probably about 15, 20 years. What's really changed for us are the materials that we build the rocket out of that are now able to have greater heat resistance and higher strength and just all around higher performance. So we can really push the envelope harder with these newer rockets than we could in the old days.
What about atmospheric modeling? How much has it helped that we can now have a better understanding both of like weather patterns down here, but presumably wind patterns up there?
Yeah, that's actually also huge. We put that together with weather forecasting and weather conditions that allow us to know what to expect so that we can model it. And something that's kind of unique to our rockets, which is our ability to reprogram our flight path when we're sitting on the pad. So if you watch a rocket launch on like YouTube and they're going through the countdown, there's a point where people are launching weather balloons. And what they're trying to find out is what is the direction and speed of the jet stream. Because when the rocket is flying at high Mach number up through the atmosphere and it encounters the jet stream, the jet stream's going to try and blow it over and interfere with its trajectory or even take it out of control. And so you have designed a trajectory like 3 months before based on what you thought the jet stream would be doing. Mm-hmm. And you're launching this weather balloon to find out if it's still true. If it's not true, you probably can't fly. But what we're doing is we're launching the weather balloon, finding out what it's actually doing. Then we run to a hardware-in-the-loop simulation lab where we develop software with the actual pieces of the rocket there. And we'll go, oh no, the jet stream is like 90 degrees off or it's much faster. Adjust the trajectory, run that through the simulation lab like 200 times, make sure everything is right. If there's any other variables, dump it into the rocket down at Cape Canaveral, Florida, and then launch the rocket and change that trajectory in real time.
How are you communicating with the rocket when it's on the ground? Are you like literally just sending code via Wi-Fi, Bluetooth?
We're plugged in, so we are physically, hardwired in.
So you're sending code via Ethernet?
Yes.
Okay. When the rocket launches, is there any way to send additional instructions to it, or is it gone then?
No, it is completely autonomous from that point forward.
So that seems like something that would be great to change, right? When are you actually going to be able to send information to the rocket instead of just modeling it up to the last minute?
Well, that's a really great question. And I'll say it's even more interesting to think about what's in front of the rocket as it enters space. LEO's a very different place than it was 5 years ago.
Mm-hmm.
LEO has 10 to 20 times more satellites than it did before.
Yep.
And flying through those to an orbit above LEO now is a lot more complicated. Today, the launch opportunities are suddenly very restricted because we're looking at where all these spacecraft are. You never know exactly where they are because their position is a little uncertain. And we're avoiding potential collisions. And we end up with sometimes, depending on where you're going, I've had launch windows that were 2 hours wide that had an opportunity like every couple of minutes collapse to 30 minutes with literally 2 chances to launch.
Yeah.
And what I'm really avoiding is not the satellite, it's the uncertainty bubble of where that satellite might be. So what I really, really want to do is have the rocket have some more autonomy to be able to do collision avoidance on its way up.
Surely the rockets of the future, they'll include some kind of signaling device because the rockets up there don't want you to hit them either.
No, they don't.
So how do we solve that problem? Presumably, there is a way to put AI modeling and autonomy into these rockets or into the satellites that are up there or into the rockets that are shooting through there.
Well, I think it's both. So we want to have the rockets aware of what's in front of them. So that's sensors and potentially autonomy. We want the satellites to know what's around them. There's a lot of talk about proliferated, we call them proliferate because there are lots of them, proliferated constellations of satellites that have some onboard AI autonomy, but they don't actually have sensors or beacons. So all they're doing is reacting to an ephemeris that got loaded to them maybe as much as 8 hours ago. And they're calculating where everything is now, and they're maybe autonomously making a course correction so they don't run into anything. That's great, but what we really want is sensors so they can see what's around them. It would be great to have satellites with beacons so that they're telling everybody, like airplanes do, hey, I'm here, this is my position and speed. And then feeding that data into autonomy to AI to make those course corrections.
So why can't we do that soon?
Well, I think we can do it soon. It's a matter of investment to have the technology, and then it's a matter of manufacturing the stuff and getting into the pipeline of what's going to space.
Okay, why not put adaptable software on the rocket itself so that in flight it can adjust its trajectory based on sensor data?
I'm going to do that.
Okay.
But I have a couple of things that are more useful I'm going to do first. So it's got to wait.
Tell me what's more useful and then tell me why you can't do this now.
So, because there's so much more stuff going to space now, the launch rate is really a very important thing. And so we want to be able to turn the rockets and fly them faster. That's one of the useful things about reusability of portions of the rocket, because you get them back, you don't have to manufacture a new one, and it helps support your higher launch rate. So the technologies that we'll do first are really about that.
About catching the rockets when they come down?
Yeah. Now, my particular kind of rocket, the one that we just finished developing, it's one of those high energy rockets. So you can't save half your propellant and separate and then fly home and land. Because if I've flown all the way to space, that would be a big, big impact. So instead, we're going to burn up all our propellant, and then we're going to separate pieces of the rocket off that are expensive and bring those back to Earth and reuse those. So we're working on that first.
Wait. How do you bring those back to Earth?
A really cool brand new technology we developed together with NASA called, here comes an acronym, HIAD, HIAD. It's a hypersonic inflatable decelerator. So think heat shield. So when a capsule comes back from space, it's got this big, thick, graphite composite heat shield facing the wind, and it's glowing red, and pieces are coming off, and it's burning back, and then it lands. That's how it's been done all these many, many, many years. But it's big and it's heavy and it's rigid. So say I want to bring my engines back from my first stage booster. I would have to put this in front of the engines, literally in front of the plume. They're blocking the exhaust of the rocket engines. So you can't do it. But if you have this inflatable device, you can deflate it, package it up, stick it in a corner, and then when you want it, you inflate it, and then you bring it back.
Okay. So you've built that, and you're now able to save and reuse parts of the rocket.
Exactly.
All right. So you're clearly sending lots of satellites into space. You're clearly going up even higher. Have you ever sent something to the moon?
Yes, we have. Yeah, we've been to the moon. We've been to Mars.
You've been to Mars?
All of America's missions to Mars were flown by us.
I didn't know that.
20.
Okay.
Yeah.
So when are you going to fly me to Mars?
Ooh, when do you want to go?
I think sort of towards the end of my life, since I assume I won't be able to get back. So I'm 50 now, maybe in like 25 years.
Oh, yeah, no problem.
No problem. Okay, here's this. When will we be able to get humans to Mars, and when will we be able to get humans back from Mars?
Well, the two-way trip is the trick.
Right.
So since you want to come home, I'm with you, by the way. I wouldn't mind going, but I'd like to come home. I don't want to go to Mars to die.
Yeah.
The two-way trip, we're talking probably 15 years because we want to go to the moon first to get really good at this and learn how to do it, because the moon is only about 3 days away.
Yeah.
Mars, without new forms of propulsion, which we're working on them, but today with chemical propulsion, it takes about 9 months to get out to Mars. So that's a long trip.
Yep.
And you can't come and go except every 26 months because the Earth and Mars are in different orbits. And so for a good portion of this 2-year span of time, we're on opposite sides of the sun. So you're not going or coming back.
That's a hard journey.
Right.
That's like worse than going through Midway.
And remember, Mars doesn't have really an atmosphere to speak of. It's like 3% of the Earth. It's like super, super thin. So there's no protection from radiation. You are going to spend 3 years in deep space radiation, which is 10 times more intense than the astronauts in the ISS. We got to have this right before we send people there.
So you think that we are likely to find convincing evidence that there was or is life on Mars?
Was is probably the more likely case.
Yeah.
I wouldn't rule out is, because our recent research on Mars has revealed the likelihood of subterranean liquid water. We didn't know that was there before. And in fact, it wasn't very long ago before the polar ice caps were thought only to be frozen CO2. Now we think there's frozen water there as well. So if we can get under the surface into this liquid water, we may find actual life. But of course, what's most likely is that there was life in the past when Mars still had an atmosphere, had liquid water on the surface. There will be evidence of that, and we have a chance to go discover that if we stay on it.
It wouldn't be hard to send a human body to Mars. It's just hard to keep them alive in the trip and then when they get there.
You got it.
Huh. Okay. Clearly, it would be cool to send humans to Mars, right? It's like satisfying a vision. But it also seems potentially useful for the species. How do you feel about sending artificial intelligence robots that mimic humans to Mars? Do you feel like that is an existentially valuable thing for humankind?
Well, it is, and it always is, the way I think about it. It's not necessarily about the AI. The AI just makes these things more capable. Mm-hmm. We always go first with robots, right? Every autonomous vehicle is a robot because, we don't have to risk a human or bring all of the kind of overhead to keep a human alive when we do that first exploration. So we've sent 20 robots to Mars already. Then when you finally send people there, now you're bringing automation machines, AI-driven robotics to help the people be more effective when they're in space, because it's really, really difficult to do anything. I mean, you can ask any astronaut who has done a spacewalk, it's just really hard. The equipment, you're in zero G microgravity, but the equipment is bulky and it's difficult and it still has inertia and it's uncomfortable. It's hot. It's just terrible. And the more automation that is there, the more effective the people are. And then, of course, there's some environments where you're never going to send people. We launched the Parker Solar Probe that's flying through the atmosphere of the sun right now. That's never going to be a human mission.
So you send up the Mars rover and you send out these little robots that are optimized for Mars. Is there an intermediate step where you're sending humanoid robots that look and talk and act like humans?
Yeah, absolutely, because that's something that's a really important advancement in robotics that we might be able to do that. The big difference, think of it this way, the big difference between the robot historically and the person in a mission in space is that robots can perform any predictable single thing better than a person can, because you can design it that way. But a person can do almost anything. So when you go into an environment that's not predictable and problems come up that are surprising to the mission planners, you've got a human there who can solve it and deal with it, partly because of their flexibility of their thought processes, their cognition. But we have hands, we have legs, we can do things. So there are times when the robot would just fail and get stuck when the person could overcome it. In between that, two poles that we've had all this time is the possibility for a humanoid, artificially intelligent, or at least AI improved or augmented robot that has more flexibility than a traditional robot, still less than a person, but able to do those really cool things that would have stymied the robot.
How far are we until we have humanoid robots on Mars?
Well, that's probably more like a decade.
A decade. Well, it's only 5 years before we have humans up there.
Yeah.
So
we'll send them first.
Do you think that there is conscious life anywhere else in the universe?
Oh, absolutely. It's a gigantic universe. The problem is, that I get asked about this all the time in the context of UAPs, unidentified atmospheric phenomenon. But just think UFO. Do I think that intelligent life has been here? I doubt it. I don't think so. The universe is incredibly big, unimaginably large. Our galaxy is unimaginably large. And we, quite frankly, we live in the boonies, man. We're out in the middle of nowhere. We're on the edge of the local void within a larger void. The distances are immense. So, no, I don't think we've been visited, but absolutely there's life.
Okay, so let's take as a premise that there's life, or there's very high odds of life. We have now created this incredible intelligence through AI. What are the ways that we can be more efficient in sending out evidence of our life? Like I remember 30 years ago, this mission where they sent out a Glenn Gould plays Bach, right? And sent that out into space. What should we be doing with AI right now to signal to other intelligences that we are here out in the boonies on this nice blue planet? Assuming we want to meet them, right? Maybe we don't want to meet them because they might eat us. But assume we do want to meet them.
There is a school of thought that looks historically on this planet where advanced cultures have met cultures that are less technologically advanced, and it's rarely gone well. So that's a valid concern. But,
right, we're like chickens out there, like, are there humans anywhere? Let's find the humans.
So be careful. But anyway, let's go for it, because I want to meet them. I'm sure you want to. I'll take my chance, and we'll meet them. So we have to send data to them.
Right.
And right now, speed of light's the fastest way we know how to do that. If we think we have access to particles here that are entangled with particles very far away, that's instantaneous. First off, we don't know how to find them. Secondly, we don't know how to deliberately encode information. But so let's just stick with speed of light for the moment.
Yeah.
Radio signals, optical signals, whatever. The big challenge is conveying a large quantity of data and conveying it in a format that a completely alien intelligence would be able to decipher.
Right.
And that's a great place for AI to help us, because the tremendous power of AI is its ability to handle massive quantities of data. And to solve this problem, we're going to use a tremendous amount of data to try different things, calculate what this best format would be, and then send a bunch of data the most efficiently way possible.
What about using AI to receive intelligence? What can we be doing now that we couldn't do 10 years ago to identify signals that may be out there?
What AI can do for us today is handle massive quantities of data, sift through it, organize it, find weak signals, find desperate little bits of data and bring them in and analyze them. There's a lot of information hitting the earth every second from all around us. And the ability to sift through that is a huge bottleneck. I mean, it's almost unimaginable what it would take to find a signal like that from the data we have. AI can do that for us. And then what's more, when we bring the other cool thing that's going on in computing right now, quantum computing, what quantum is super, super good at is breaking encryption and searching unorganized or unstructured databases. If we can bring those two together, not only might we find the thing, we might even be able to decipher it and understand it.
Oh, that's so interesting. So you think that the abilities of quantum to break encryption, which is its ability to do higher order math that, undoes the math that created the encryption, you think that could be useful for figuring out the signals coming in from outer space?
Yeah, absolutely.
I've never heard that argument before. I love that.
Well, think of it this way. You've probably heard of the code talkers in World War II, right? Navajo Indians, very different language. Nobody could break that because the language had no common elements or ancestry to known languages. That's what made it a code. Well, if there are alien life forms that have developed completely independently of anything here on Earth, far, far away, and we receive a message from them, there's a pretty good chance it's going to be more alien to us than Navajo was to the Japanese.
Right. So we can use quantum computing perhaps to understand it the way we can break codes. We may be able to use AI to create our own language that we send out there in a way that will make it more decipherable for them. And maybe they'll have a quantum computer and they'll be able to decipher it anyway. Okay, amazing. This is a question we ask all our guests. What's the most surprising or interesting way that you've used AI in your life recently?
Oh, really? Oh, that's a great question. Yeah, so we have been using it in our factory to do kind of two things. We have a Gen I application around maintaining chemicals, complicated chemicals we use to process a rocket. And then we have classifying AI to deal with quality things we do on this really complex rocket. And I anticipated using them in a certain way, and I have been very surprised at how people have interacted with the tool and what the tool generates. Humans make these leaps of intuition and see patterns because we've evolved to see patterns. We're really good at pattern recognition. We can see patterns when patterns don't exist. That's how good we are at it. And ways to use these tools, which I won't go into specifically because it's a little proprietary. It's kind of cool. That we never imagined.
Wow. All right. That's very cool. That is an excellent answer to that question. All right. Tory Bruno, thank you so much for joining The Most Interesting Thing in AI.
It was absolutely my pleasure. Fun conversation. We'll do it again sometime.
Awesome. We'll do it on Mars.
Awesome. Yeah, I like that. But only when we can come home.
Yeah, that would be better. We're going to take a quick break, but when we come back, I'll be joined by Joe Schurman, co-lead of PwC's U.S. space program, to talk about where AI is most beneficial in the evolving space market. Joe Schurman, thanks so much for being here.
Thank you very much, Nick. Appreciate the opportunity and the time.
So first of all, tell me a little bit about what you do for PwC.
First of all, I'm a principal at PwC, but I led the firm's AI services for the aerospace and defense sector. So most of my clients were space-related clients as well as general aerospace and defense leading organizations.
So tell me, you've got a lot of stuff you're building, it looks like, in your home office. Tell me something crazy that you've built in the last couple months.
I've got a few projects ongoing. The craziest one, the most fun project I've been on so far, has been developing a mobile AI sentient agent. So basically what I've put together here is a Raspberry Pi 5 and now a Jetson Orin Nano device that has its own mobile large language model that is running natively on the device. I've also equipped it and integrated a sensor array so it can understand what's around it in terms of environment, and then several computer vision cameras so it can understand what it's seeing. And you can interface with it using voice, you can interface with it using chat, or if it's on a satellite controller or drone, you can use a ground station terminal chat-based service. And recently, a buddy of mine from Space Force and I actually launched the device on a space balloon. So we actually took the device a little over 100,000 feet and had some really good footage that was covered by that. But now we're focusing on drones and then eventually in a CubeSat format for satellite deployment.
It's a kind of personal intelligence, like a mini robot brain, and you're launching it into space.
Yeah, so think about taking the AI brain out of a robot and putting that into something that can actually fly.
Wow, very cool project. So we just heard from Tory Bruno, the CEO of ULA. What do you guys actually do with ULA?
Well, PwC has been around for over a century, and we're traditionally a tax and audit firm. But we have a very large advisory and consultancy part of the organization with business or vertical industries like healthcare, financial services, et cetera. We're out in front quite a bit as being kind of client zero for a lot of new technology. We were one of the first, if not the first, firm that adopted OpenAI's ChatGPT service for the enterprise.
I remember that.
And we have a very strategic relationship with OpenAI and Microsoft on that, but we're also multi-vendor AI at this point. My team specifically, we were focused primarily on the aerospace and defense sector. I also had a specific focus on space. Myself and another partner, John May, actually worked together to create our space program here in the US. And so a majority of my clients are actually space clients, including United Launch Alliance. From a foundational perspective, most of these organizations have not been able to leverage or really entertain the artificial intelligence services that are available to the commercial market. And so in the public sector market, these services, as far as like basic chat against a large language model like you would have with ChatGPT, wasn't available until the past year. So we were helping them onboard which technologies to leverage based on specific compliance related matters that allowed them to use these tools to begin with.
Oh, that's interesting. So when Tory's trying to figure out what software to use, he's quite hamstrung. He has to figure out the particular model and the particular way it complies, and then you also have to presumably adjust it so that it's more secure.
That's correct.
And you're working with him to do that.
And other clients as well, because it's been very difficult to enable AI within the public sector. You're just now seeing most of the public sector adopt the ChatGPT government solution as really kind of their first iteration into that space. Before that, they were looking at opportunities to entertain kind of private cloud or even container-based AI services where the large language model is not publicly exposed, kind of like my mobile AI sentient device that does not have a public connection. So those services are highly customized, deployable AI models that have no internet access whatsoever. The solution could actually sit on a rocket in a CubeSat.
What is the coolest thing that AI now enables in the aerospace industry?
Overall, agentic AI is the latest capability that organizations are integrating into their platforms. And what that really does is it can even awaken older applications that had not been used that still have value by creating an agent that has access to its data or to its workflow and presenting that in a new way that's more modern. That's part of the product suite that we're actually enabling for our clients more broadly, is more of like agentic access to those capabilities.
So there is a PwC report that the global space economy may grow to as much as $2 trillion by 2040, and it'll be primarily private companies, not government, who'll be taking the lead. Explain how you see the market evolving.
Well, I'm not an economist. I'm an AI engineer, but I'll tell you what I think. I would say the biggest change is the ability to include the private sector into space and enabling more of that wide range of organizational capability, and also like the up and coming, think tank startup organizations. You're seeing a lot of uptick in that capacity as well. It's just opening up the market more broadly versus a handful of approved gigantic public sector contractors, which I have no issues with those contractors, but it's very limiting in terms of the ideation and other services that are being brought to the market. So I think that's the biggest opportunity. And I think the cislunar market is going to definitely pop up. One of my colleagues who helped write that report that you're referring to, we joke back and forth, but there's this one market economy that I'm really stuck on because I'm a Texan, and I can imagine space trucking, being a pretty interesting economy itself between the cislunar market.
How many people do you think are going to be living on the moon in 20 years?
No idea. But I will say that the amount of infrastructure that's required to get there is significant. And just to coin a phrase from one of my favorite people that I work with today, Dr. Travis Taylor, If you look at a highway and you see all these objects that are along the highway that basically provide reflective light for the drivers, just those lights, there's millions of those lights. Imagine the similar application of that type of infrastructure development that's required to actually build an infrastructure on the moon or Mars or other locations. It's a significant undertaking.
What is some of the most interesting infrastructure we should build on the moon? Like, what is the moon particularly good for?
I see planets more as a gateway to understanding deeper intelligence. We're still at these very early stages of exploration, but I think leveraging them as a gateway, enabling them almost like a Wi-Fi access point on each individual planet to transmit information across planetary travel and our deep space reconnaissance type intelligence gathering satellites as well.
So we should be setting up like satellites, information gathering sessions, using them as like embassies as we explore the rest of the solar system.
Correct. I agree with that.
Huh. What is the most surprising or interesting way that you've personally used AI in your life recently?
I use it daily. I use it to actually perform almost every daily task.
Are you using it right now?
Not at the moment. Not at the moment, but I have it in the background just in case I need it. But no, I mean, there's an avatar out there that's actually doing something on my behalf.
What is it doing? Is it ordering your groceries? And what's it doing for you?
Yep, all of the above. Writing
Really?
books, giving me content ideas, researching specific subjects. And
Wait, go back. Writing books? You have an agent out there writing books?
I've written a couple books and I have no time at all to write another book. And so I started toying with the idea of maybe doing another one. I've uploaded my books digitally to a specific model, and I've trained it on how I write and how I think. And there's been a lot of instruction that I've provided to it. So it refers to me by nickname. It actually knows the way that I think and talk in a lot of depth, actually. So it's giving me excerpts and I'm reviewing them and then improving them or making, small edits to them. So the whole process is a lot easier this go around.
Well, if you write 900 books next year, we'll know how that happened.
No. We're talking about one, maybe two.
Joe Schurman, thanks so much for being here.
Oh, thanks, Nick. I appreciate you having me.
This has been The Most Interesting Thing in AI. I'm Nicholas Thompson. If you've enjoyed what you've heard, please rate and review this on the podcast platform of your choice. And tell us what kinds of AI-related topics you want to hear about and guests you want to hear from. Your input helps us make a better show. Also, make sure to hit the follow button so you can be alerted of future episodes. Next week, I'll be joined by Navrina Singh, founder and CEO of Credo AI. She tells some of the world's largest companies how to manage their AI risk.